Great. Thank you very much, Dr. Meakin. I'm really pleased to be invited and really excited to talk about some of the research that we're doing at Cape Breton University in the area of biochar. And so just before I get started, I just wanted to talk about the title a little bit. So reaping the unsown benefits of biochar comes from sort of the historical nature of biochar being really rooted in agriculture. So biochar has been used for thousands and thousands of years to enhance soil growth. You might know about people, for example, burning their lawns to get a greener lawn in the spring or summer. You might hear about people putting charcoal into from their fire pit into their garden to help with growth. That's a really, deep historical use of biochar, sort of that fixed carbon content in the soil to help with agricultural purposes. Talk about that a little bit, but really my expertise is in materials chemistry. And so we see biochar as having a lot more potential than just as a fixed carbon source that we can bury in the soil for agriculture. And so before I start, I just wanted to mention where I was coming from today, because South Carolina is, although it's on the same coast, quite a distance from Nova Scotia. Nova Scotia, Canada is located this little peninsula at the very sort of top of so you're down here in South Carolina region, and we're up here in sort of what you call the North Atlantic. But Cape Breton is actually this little U-shaped island that is actually not physically attached to Nova Scotia. It's part of Nova Scotia. And I'm located at the very tip of this part of the island right here. So it's only 11:30, so I think it's a 1 hour time difference, which is, incredible considering the distance. But I don't know if you've been before, but we are the #1 island in all of Canada, which doesn't have that many islands. But it's a great place to visit, especially in the summer or the fall. So I welcome you to come visit us in Cape Breton. I also wanted to mention the fact that the research I'm going to talk about today is coming from an undergraduate institution. So we don't have a graduate program in chemistry or engineering. All of the research that we are doing has been done by mostly undergraduates. This is a picture of our group from a couple of summers ago, and postdocs that have been in the lab for several years that help run the lab. This is a picture down here of our group that we went hiking last summer. So all undergraduate students working usually in their second year, they'll start in the lab and they'll work part-time during the year and full-time during the summers. And they really get a great experience. It's almost like a master's student experience working in the laboratories. And we are also grateful for the funding sources to help us do this research. So essentially what we do in our lab is we burn stuff. We have some great fun with that in terms of, taking pictures and making funny schemes about our research. But we take what is considered to be a waste stream, mostly local, although we are working with a group out of California right now who have sea urchins as a problem. So local definitely does not include California for us, but we typically deal with local waste streams like the aquaculture waste. In the case of today's talk, I'll speak mostly about snow crab waste, as well as forestry waste. And we find higher value use for this waste other than just landfilling or composting, and not really using it to its full potential through a process called pyrolysis to generate 3 types of materials. Really, we generate a liquid, a solid, and a gas. But what I focus on in my lab is most of the time is the solid, and that solid is called biochar. And so the goal is to, yes, look at whether or not we can use biochar in soil as a potential enhancement material, but also as potentially a remediation material. We've also looked at biochar in the material sciences. I'll talk a little bit about that today in terms of using it as a replacement material for things like, for example, Portland cement. We are really interested in this field where we can take biochar and do some chemistry on the surface of it and make it an interesting catalyst for reactions. So rather than generating really expensive materials for catalytic reactions, for example, in industry, can we use a waste material to generate the same kind of products? And then, of course, we have done some work in agriculture as well. Before we get started, though, I want to talk a little bit about what biochar is. So this is the official definition of biochar. It's carbon, it's charcoal, it's all those, pretty popular common names that you might think of when you think about like a black substance you can hold in your hand after you've had a fire. The official definition is it's really boring. It's a porous carbonaceous solid produced by thermochemical conversion of organic materials and oxygen to blah, 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 blah. Really boring. Nobody wants to hear that. It is a porous material. It depends, its porosity depends on the biomass that you start with. But for example, when you're talking about woody biomass, because we don't heat to super high temperatures, we're able to retain a lot of the original porosity that's inherent in the organic biomass. So you can generate materials that have, it almost looks like a molecular sponge. So you get pores that are similar to the pores present in the original biomass. They may be linear pores. There could be porosity that goes in between the walls as well. And it is almost always a high percentage of carbon. So typically it's a fixed carbon. But again, biochar is generated at lower temperatures than, for example, activated carbon is generated at. And so because of that, we also get a combination of other elements present, such as oxygen groups, maybe nitrogen if it's coming from an aquaculture source. But also you may have some volatiles and water present as well because we're not heating to super high temperatures. So basically we take an organic biomass source. It's typically dried prior to use because you can't have a very high water content if you want it to burn. You burn it in an oxygen depleted environment. So we typically recycle the gas that's produced during the pyrolysis process back through the unit to deplete the oxygen and prevent complete combustion, because you don't want to just generate an ash. And then you end up with this porous carbonaceous material that may have a certain concentration of volatiles depending on what you're starting with. You might have some water in there. And if your starting biomass has a lot of minerals, you may have a certain percentage of ash as well. But largely it's carbon pores. So this is a schematic of, or two schematics really, of different pyrolysis units that sort of describe the general process. So your feedstock goes in. Typically, there's a drying step before your feedstock goes into the pyrolysis unit because you have to have a less than 20 to 30% water content in order for it to burn. It goes into a unit that has some sort of ignition or fuel source that will burn your biomass. And again, this is under an oxygen depleted environment. So thermochemical conversion occurs here. You're breaking apart the biomass, the lignin if you're talking about woody biomass, the proteins if you're talking about fish biomass, and it starts to break it apart, and you'll get essentially three groups of compounds formed. You'll have large compounds that are too big to be volatilized. So they will be collected through some kind of filtration unit. Maybe it's a cyclone that will pull out the solids. It could just follow to the unit if it's a different type of system. But in general, you'll collect biochar here. Then you'll have the molecules that are a little bit heavier than gas, but not as heavy as a solid. And they'll be collected as an oil or water sample. And so that'll be siphoned off and has a lot of high value applications that I'll just briefly touch on tonight as well. And then, of course, you'll have the smallest molecules that can't be condensed into a liquid. And you can either off-gas those, that's not the greenest approach, or you can recycle them back through your unit as a syngas that could be burned, or you could collect them in some sort of filtration unit. So you can imagine that pyrolysis could technically be a very green process if you're able to put in a 100% carbon content, collect all the solid carbon, collect all the liquid carbon, and somehow filter off and collect all of the gaseous carbon. And that would be better than allowing, perhaps in some cases, the waste biomass to sit in a compost facility and just degrade over time and release that carbon back into the atmosphere as CO2 anyways. So we deal with both crab and woody biomass. I'll talk about the crab first because it's quite an interesting story. So I showed you where Cape Breton Island was. It's an island off of the top part of Nova Scotia. A lot of our economic structure is built around both forestry, but also aquaculture. And so on our island alone, we have 5 major crabbing facilities where snow crab, which you can see in this image here, is fished 5 times a year. And during that time, fishing is essentially 24 hours around the clock for 6 weeks out of that time. And the process involves, sorry, this is a little bit disturbing maybe, but it does involve tearing the shoulders and legs off of the crab body, and the central part of the body is considered waste, and so it's wasted or discarded. This is discarded. This bottom right-hand image is a picture of what that central body part looks like when it's discarded, and then it is put into a transport truck. One daily leaves from Cape Breton Island, and it travels off of our island onto the mainland to a landfill facility that will accept this crab waste, because as you can imagine, you can probably even look at this picture and see how much it smells. It doesn't smell good, and you can't have this around any neighborhoods or public places. So it's a long transport. It costs a lot of fuel to transport the waste off of the island. It's a big cost to the crabbing facility. It's a big carbon footprint for them. And they're actually transporting a lot of water because this is high water content waste. And so that's also a big waste problem for them. And in fact, the government has told the crabbing facilities in the North Atlantic that they have until 2026 to find a solution to this problem, because landfills and compost facilities are no longer going to accept the crab waste. It can't all go back into the ocean because it's composed of highly basic components like calcium carbonate that changes the ecology of the ocean if you dump all that waste back in. And so there has to be another solution. And also it could be a higher value product. So we started working with Lewisburg Seafoods, which is a particular crabbing industry, the biggest one on Cape Breton Island, about 7 years ago, trying to figure out what we could do. So we get pieces that kind of look like this top left-hand corner image. This is actually, this would be considered a pretty nice sample. And you can see the legs and the shoulders. Sometimes there's rocks and shells. It's very heterogeneous. We'll get seaweed in there as well. We dry this material in a regular oven. And so this is the biggest hurdle for this research at the moment, because this drying process, it takes quite a lot of time. Typically we dry for 2 to 2.5 hours. And we're removing up to 70% water during this process. Now, the good news is that the removal of water, the drying and grinding, creates a really stable product. So this crab powder, it doesn't have the atrocious smell that the crab waste has. It doesn't smell great. It smells kind of fishy. But it also doesn't decompose very readily. So it will slightly decompose over time, but we've stored this stuff in the lab for 4 or 5 years without much decomposition. That's because it's largely composed of calcium carbonate, which is a stable base. And there is some proteins and chitin in there, but we have calculated based on some experiments that it's about 60% calcium carbonate and then other proteins, amino acids, and carbon-based materials. Then we undergo a pyrolysis of this dried material, and we make what we call crab char. And so crab char is shiny. It has a kind of a shiny glitter to it, which other biochar doesn't have. And we've done a lot of work to see if there are applications both of the crab char itself, as well as the dried crab powder. And that's what I'll talk about a little bit today. We also have done some work because, as I mentioned before, if you recall, pyrolysis generates 3 products: a solid, a liquid, and a gas. So honestly, at this moment, we off-gas our gas just because that's the easiest thing for us to do. Ultimately, if you want to put this into an industrial setting, you want to collect the gas so you're not generating greenhouse gases. But the bio oils themselves are very interesting. So you get a very thick, oily layer and a more thin water-based layer, which actually has a lot of interesting compounds in it, including indole. But the crab oil itself is quite interesting. So Haley Oliver was an honor student who did some work on the crab oil. She found there were a lot of really interesting chemicals present, like some phenols that could be used in resin formation. But the cool part is that she was able to measure the energy associated with this crab oil. So, of course, we are all facing a fossil fuel crisis in the near future. Of course, I don't know the solution to what we're going to have to do to move away from fossil fuels, but I anticipate and expect that the solution is not going to just be one solution. We're going to have to look at many different avenues for generating new fuel sources. And bio-oil is a potential alternative fuel source. Woody biomass, bio-oil, has a lot of background literature that's already been published indicating that there is potential. And in some of the northern parts of Canada, woody biomass, bio-oil is actually used as a bunker fuel already. So it's not out of this world to think that you could use bio-oil as an energy source. But that woody biomass bio-oil, it has a higher heating value of around 17 or 18 megajoules per kilogram. So a higher heating value is essentially the value we measure for oils to tell us how good they are at providing energy. So it's a measurement of energy per mass of the oil source. So just to give you something to compare it to, a bunker fuel from fossil fuels has a higher heating value of approximately 40 megajoules per kilogram. And so again, that's fossil fuel bunker oil. Then if you look at forestry bio-oil, it's around 17 megajoules per kilogram. And the crab bio-oil is up around 30 megajoules per kilogram. So it already has a lot of promise as a potential alternative energy source if there is enough biomass produced to generate it, as maybe, for example, it could be an energy source for just fishing boats alone. It wouldn't be able to replace fossil fuels, but it might have some potential as an energy source. It's interesting. It does have a high water content. This is something that is workable because there already are ways to remove water from oil. But what's really cool about it, and not unexpected, is that it has a high pH. So typically fossil fuel oils are around neutral pH, sometimes maybe slightly basic. Forestry oils are really acidic because a lot of trees that forestry biomass comes from, they contain polymers and large molecules that when they break down through thermochemical conversion generate acetic acid. And so their pHs are really acidic. That's a problem for using them as replacement oils because they'll be corrosive to the infrastructure that already exists for burning oil, whereas crab oil has a basic pH. This is probably too basic, but it's an easier problem to deal with than acidic. That's not why I'm here today. I'm here to talk about biochar. So just to give you an idea of the kinds of yields we get, there's two types of pyrolysis we can do in our lab. There's more than just slow and fast pyrolysis, but I'll just talk about those today. A slow pyrolysis involves a slower heating rate. So you might go up 20 degrees per second versus 70 degrees per second for fast pyrolysis. And typically slow pyrolysis is held at a much longer heating time, so hours compared to minutes for fast pyrolysis. And usually you use slow pyrolysis if you prefer to get a higher yield of the solid product of the biochar. And fast pyrolysis generates usually a typical higher liquid yield. And that's just because you're hitting it quickly with high temperatures and you're blowing all the volatiles off before they have time to recondense and turn into a solid through that thermochemical conversion. And so with crab, we see approximately the same char yield, but we do see a slight increase in the oil yield when we use fast pyrolysis. versus slow pyrolysis. You can see with the, this is Dr. Ali Shafi, who is a postdoc in my lab for the last year. He's a great mentor for the undergraduate students, a very hard worker. And he has been able to do a lot of this work in the Crab BioChar project. You can see that the Crab BioChar by the microscope image here, it doesn't look the same as the woody biomass biochar I showed you on the previous slide. The pores are different. They're more similar to what we see with the crab shell structure. And this is a chitin protein network of carbon-based materials creating these pores, as well as larger chunks of what we assume is calcium carbonate salts that occur around the surface. One thing I should say about the crab biochar compared to woody biomass biochar is that it has a much higher concentration of ash. The ash content comes from the calcium carbonate being such a high concentration in the crab bodies themselves. Okay, so we've done a lot of characterization. We had to show what the material was made of before we could really look at the potential applications for it. The crab biochar is also basic. It has pHs around the same as the oil, and it's about the same pH as you would expect from dissolved calcium carbonate, which is a base. It doesn't have a super high surface area. So we didn't talk much about surface area, but the biochars that we make with woody biomass, they typically have surface areas around maybe 400 meters squared per gram. So that's like a decent sized living room in your home, or maybe living room plus kitchen. Activated charcoals are, or maybe even a decent sized small home, actually. Activated charcoals are around 1,000 meters squared per gram. That's like the size of an Olympic swimming pool on 1 gram of charcoal, like a stick of gum. And so these surface areas for crab char are pretty small, 28 to 16 meters squared per gram. It's like a closet. But it's still a significant surface area. It's not nothing. What we can see, this is an FTIR spectrum. You can see that the green curve is a curve spectrum for calcium carbonate itself, and the yellow is crab char. And the peaks overlap and are consistent with what we would expect to see from calcium carbonate. This big peak here and this big peak here, which are indicated by the red arrows. But also we see calcium oxide formed in the crab char. And that's likely because we are reaching some critical temperatures during pyrolysis that are able to convert the calcium carbonate into calcium oxide at high enough temperatures. We confirmed this with XRD. We don't need to get into that. So let's look at some of the applications. We talked about remediation, materials additives, catalysis, agriculture. If you're familiar at all with Cape Breton, or if you've ever read a book about Cape Breton Island, it has a rich, deep history in coal mining. Really, that was the original industry associated with Cape Breton. So even if you look Cape Breton up on the internet, you're going to hear all about the coal mining industry. And so we actually, this is probably maybe going to be a shock to some people, I don't know, we still burn coal for our power supply in Nova Scotia. And that is going to change in the next 5 years, but Cape Breton currently only has one active mine, coal mine, and it's actually run by a United States company, but it still has a significant coal mine remediation issue. So all the coal mines that were mined in the 30s, 40s, 50s, 60s, 70s, 80s, they were not properly treated a lot of the times upon exit. And so we have a lot of offings of the coal mines, this coal mine water, acid mine drainage, that is very acidic. It has a pH of about 3. It contains a lot of minerals and salts like iron sulfates and aluminum oxides, magnesium sulfates, and copper sulfates. So this is a big problem for the watershed. So if you're ever walking along a beach in Cape Breton, you almost always will notice this sort of orange offshoot that comes out of the cliff. And that's typically coming from a flooded coal mine. And so this is a local, we're dealing with a local waste, the crab waste. We have local remediation issues that we might be able to solve a problem for. And so that's where our interest really went in the beginning with the crab char. And so Chantal Mercer in the red hat here, she's a graduate student, a chemical engineering graduate student in my lab. And she's a single mom with these two awesome kiddos. And she's just finishing up her master's thesis right now. And so part of her project was to look at whether the crab char was able to neutralize this acid mine drainage that we have in Cape Breton. And she looked at both the dried crab itself and also the crab charcoal, but I'll just talk about the crab charcoal today because they both performed pretty well, actually. The difference was that the charcoal required lower concentration. And so what we have plotted here is the pH of the acid mine water versus the thyme, and the different concentrations of crab char that we use to try to bring the acid mine water to a neutral pH. So we started with 0.05 grams, which is a really tiny amount, right? 50 milligrams of crab char in 100 mils of acid mine drainage that had it started at a pH of 3. And after only about 1 hour, we got to 5.5, getting close to 6, a pH of close to 6. So this was a promising result. So that's a pretty big leap in pH. As we increased the dosage, only to 500 milligrams, half a gram per 100 mils, we were overshooting the pH. So really, we want to look at a neutral pH. So we're somewhere in between a 0.1 and a 0.2 grams per mil dosage of crab charcoal to neutralize this pH. And so this is, I sort of was talking to Ben about this problem that I think academic chemists have sometimes, is that we'll do this kind of research and not think about like the actual applications. The fun part is that we're working with some local industries who are helping us think outside the box a little bit in terms of, okay, yes, you can take a beaker and put 100 mils of acid mine drainage in it and add 0.2 grams of crab char and you neutralize the pH, but how do you do that in an actual mine? So we're working with some engineers on that, trying to solve that problem now, which is kind of fun. We've also looked at the fact that acid mine drainage, it's not just acidic and corrosive, it also contains metals that are toxic and dangerous to be putting into the ocean. Copper is one of the worst things we can be putting into our oceans and poisoning our fish with. And so Chantal has looked at copper removal versus sulfur removal, because typically these copper and iron salts are sulfates based on the geology of the land in Cape Breton. And she's been able to show that we're also able to remove the copper much better than the sulfates, actually, which is an interesting chemistry question to look at that we're going to look at. But we see a much better percent removal of copper than we do sulfates. We thought it would be pretty consistent, but it seems to be selective for copper. And this is, we did some thermodynamics, and we're able to show that as we increase the temperature, which is what happens in these in these closed down mines, is they start to warm up and the temperatures start to increase. With the presence of the crab char, we actually get a negative delta G. So this is a favorable process as well. So that's good. That's interesting. It's good. We've done the same kind of experiments with iron, and we see very similar results. Now what we need to do is look at whether there's a competition between the copper and the iron removal with the crab char. On to something completely different. Another project that we've looked at for applications of our crab char is in the area of material science. So Giomara is a materials engineer at the University of New Brunswick. And I'm not even going to pretend to be an expert in this area of concrete and cement chemistry, because it's way more complicated than I ever knew until I started talking to Giomara about this. But basically, the fishing industry, they're not interested in actually making a product out of their waste. They want some other industry to take their waste from them and either take it for free or pay them to take it. And so we had to start talking to other industries that might find value. And we started talking to a local cement industry called Lafarge. This is a Nova Scotia cement industry that's located in a lime quarry. Because as I learned about this project a little bit more, I found out that a lot of concrete is made with the incorporation of a lot of mined lime, so mined calcium carbonate. And because they use such a high volumes of calcium carbonate, they typically try to set up their industry near lime quarries. And so in the process of making concrete, they'll use water and sand, crushed stone, cement and SCMs, I'll talk about that in a second, and air. And this 11% cement and SCMs, that's the part that's interesting to us, because this process is where the mined lime, the mined calcium carbonate comes in. And so the cement is also known as Portland cement. It is a mixture of a bunch of different stuff, but also lime, and it's heated to 1,000 degrees Celsius. And oftentimes there's some sort of carbon or charcoal put into that mixture as well. And that process of making that Portland cement is really not green. It's environmentally hazardous, uses high temperatures. And of course, this strip mining process to remove the calcium carbonate from land is also not a green process. And so this is another industry where the government has asked the scientists to look at reducing this 11% with additives that are not mined lime. So we provided some crab char to Geomara, who looked at incorporating it into some concrete plugs, and then we did some testing. So what we did was we took this 11%, we replaced 5% of it with crab char, and then we looked at the compressive strength, the tensile strength, and the flexural strength to see if there was an impact. And we saw actually an increase. Usually it was around 6%, although we had some that were a little bit higher, an increase in compressive strength, tensile strength, and flexural strength for replacing just 5% of that 11% with crab char. So that replaces the calcium carbonate content that's typically put into Portland cement, as well as the carbon content that's typically added to Portland cement. This is an ongoing project we have just started in the last, just really since COVID slowed down and research has picked back up. So we're really excited about this as well. We have done, this is kind of a fun story as well. So I'm a materials chemist, and all the plants in my house are dead. So I typically try not to grow things. But I had a high school student who came to the university, and she wanted to do her science fair project with us. And she was really interested in plants. And so we said, okay, well, around here, everybody adds lime to their soil because because of the geology of our land, our rocks are really acidic, our soil's really acidic. And so we have to treat it with lime in order to grow. And so Marissa, who was a coastal action student, she said, well, can I do a project looking at whether or not we can use crab char instead of lime? And she just wanted to grow barley. So we did this, we got some greenhouse equipment from a nearby biology lab, and we did this project during COVID. Actually, she did it at our house. So she grew the same seeds in each red solo cup using the same conditions. And what she found was, this is really an anecdotal image that I'm showing you, but she did all the research in terms of determining the sugar content in the chlorophyll and all the really cool stuff that I have no right speaking about because I do not understand it or couldn't speak about it well. Anyways, but what I like about this picture is you can clearly see that with no fertilizer, she did this in triplicates, of course. She only got about 2 to 3 sprouts per cup. With lime added, she saw an increase in sprouts compared to no fertilizer. And with the crab char, she had about the same number of sprouts, but she saw much longer shoot lengths. And she also saw a huge increase in the chlorophyll content and the Brix Brix value for the plants. So there's a potential application of the crab char as a replacement for lime that's used in soil as well. And I did mention that we are materials. I'm really a catalytic chemist who likes to do synthetic chemistry on weird things. And so this is really my favorite part of the whole entire project. So we know that, biochar, the charcoal part. So if you think about the crab char, you take out all the calcium carbonate, you're left with some kind of carbon structure. With woody biomass, you don't have that calcium carbonate present ever. You have some kind of carbon structure, but you're not heating to temperatures that are high enough to get rid of all the functional groups. And so you end up with structures that kind of look like the structure here in the left box. You have some surface functional groups that might be hydroxyl in nature, so OHs or ethers, OR groups, or they can be connected to other materials. You might have carbonyls, or you could even have carboxylic acids, but there's some functionality. The problem is, this is really interesting from a chemical perspective, but it's not consistent. So even if you use the same woody biomass every time, you're going to get a different variation of oxygen functional groups. And this is difficult to, do anything with, because it's not consistent. We don't really know that we always have this hydroxyl group there, for example. And so what we've done is we've done simple oxidation of the surface of the biochar, and we were able to install a known quantity of carboxylic acid groups and OH groups. And so that the biochar is now something we can actually deal with in terms of doing some more chemistry at the surface, or we can use it as a catalyst on its own. And so this amazing graduate student, Juliana Vidal, who is now she's finished her PhD and she's now doing her postdoc at McGill University in Montreal, in Canada. She did a whole bunch of different chemical reactions to show that this kind of biochar was able to catalyze oxidations and make these really cool cyclic lactones, which I can talk about in further detail if anybody is interested, but I didn't know if this was the audience for that, so I left it out of this talk. We've also done some tailoring, though. So once we do the oxidation, so this is just another cartoon image. Tristan Snow was able to do this work. She was an exchange student in our lab last summer. Again, this first reaction is the same cartoon image of oxidation. So we take this biochar that we don't really know what it looks like on the surface, and then we install carboxylic acid groups and alcohols, OH groups, and then we can condense siloxanes on the surface and actually purposefully install amines and thiols, which we can then do more chemistry with. So we are now working on generating thioureas and sulfonic acids, but the last year we spent really characterizing this thiol functionalized biochar and nitrogen functionalized biochars that were made from woody biomass. And we've been able to do things like absorb gold, generate gold nanoparticles on the surface. We use the Aptes biochar to absorb CO2 and make some really interesting ring structures on the surface of the biochar. So this is kind of like getting into the weeds of chemistry, but it's also really where we have a lot of fun as well. And so I'm going to stop there. Just again, thanking all the people who did the work on these projects. Biochar has a lot more potential than just taking it, although it's really good in the soil, taking it and burying it in the soil and growing more prolific vegetables. There's a lot more that we can do with it. And I think there's even more than we've thought about. So I'd love to see this area grow. I'd love to see people start to really get a good understanding of the material itself and how it could be used in a whole bunch of applications from pretty much anything you can think of. Thank you again for inviting me, and I'm happy to have a discussion and welcome any questions.
Fantastic. That's a really cool talk. I'd never heard of biochar until now, and it's really cool to see all the possibilities and what you've already done with it. You mentioned that the 2 slides back, the functionalization of the biochar. Did you want to talk about that a little bit? You were absolutely welcome to do so if you want to.
Yeah. So I actually Just being a big geek,
Good.
did pull up just in
Good.
case anyone was
Absolutely.
interested. So what we have done with this oxidized biochar, so that biochar that we reacted to put these surface oxygen groups on, is so I think this is super cool because we take something that's a waste product, we oxidize it to make it an active catalyst, and then we use it in this this catalytic cycle that actually incorporates CO2 into a molecule. So we use a material that was about to generate CO2. We take CO2 from the atmosphere, and then we make these we do these cycloaddition reactions in order to make these cyclic carbonate molecules. And these cyclic carbonate molecules are really important molecules in a whole bunch of different industries. They're super important in the oil and paint industry. They're used in the battery industry. They're typically used in like the synthesis of plastics all the time. And so that was really cool that we were able to take these epoxides. So this is an epoxide. And then you can sort of see, I'll show you the catalytic cycle that we propose. This is what we use as our cartoon image of oxidized biochar. The biochar is the black circle. There's the oxidized group. You have your epoxide come in, and you get this hydrogen bonding interaction between the epoxide and your oxidized biochar. And that allows for easier ring opening. So that's the catalytic part. We're making it easier. And then the carbon dioxide comes in, inserts in the opened epoxide, inserts into the carbon dioxide. And then we get ring closure to form these cyclic carbonate materials. And so this is our proposed and published mechanism, but it's the first example of a biochar being used as a catalyst in an important reaction like this, but also more importantly in a catalytic reaction that involves CO2 incorporation as well. So, I feel like it is our goal to be this giant carbon sink that's pulling all the carbon from the atmosphere and doing something important with it.
That's super cool. That's really cool. So what temperature does this work at?
Yeah, that's a great question. So when Juliana was doing this work, she looked at the best conditions. And so typical reaction conditions for the formation of cyclic carbamates are pretty harsh. We'll use like a pressure reactor because you're anytime you use a gas as a reactant, you have to use typically you have to pressurize the reaction because you have to get the gas to go into solution. But these conditions are not bad. 10 bar of CO2, that's high pressure, but it's not like whoa,
it's not crazy. Yeah.
And 110 degrees, so it wasn't crazy.
Also 6 hours. Crazy.
Yeah. So these are the optimized conditions. And then we were able to look at a bunch of different epoxides. And so we have some scope here as well. And what is really cool, I should have mentioned this, I should add this to my general talk, is that we can then reuse that biochar. So once it comes back out of the cycle, up to 6 times without seeing any loss of activity. I think it's shown 5 here, but I mean, Juliana just got bored and then was
fair,
there's nothing. Yeah.
Well, especially if you're not seeing any loss at all.
Yeah.
That's interesting.
Yeah, it was really cool. And I mean, I have to give full credit to Juliana and also to my collaborator, Dr. Fran Curtin, who Juliana was a graduate student at Memorial University and Fran was her primary supervisor. So it was really this collaboration between my group, who's able to make the biochars and characterize the biochars, and Dr. Curtin's group at Memorial, who's able to look at these biochars as something that could be useful in these catalytic cycles. So, and
that's super cool though. I mean, it's a really nice marriage of the fundamental work, but then also an application that could be really interesting.
Yeah, it's very neat. Yeah, we're really pleased with this. So
yeah, you should be. That's super cool.
Yeah.
Awesome. All right. Well, I guess we can dive straight into the questions then. I've got a few here. So does the starting material affect the types of moieties attached to the carbons, so like ketones, aldehydes? You mentioned nitrogen containing groups.
Yeah.
Is that pretty much based off of what your starting material is?
100%. So I'll see if I have another. Yeah, this is a perfect slide.
Okay.
And so this is an image of all of the, not all of, this is 4 examples of published work showing characterized woody biomass biochar.
Mm-hmm.
And so these are the references right here, but all of these biochars were generated from different woody biomass starting materials. So it might be like softwood or hardwood. There could be, it might not just be the difference between softwood and hardwood, but it could be the difference between whether you're using a sawdust pile or a branches and leaves pile, because you'll get different organics in those starting materials. So absolutely 100%, you're going to get different functional groups depending on what your woody biomass or what your biomass starting material looks like. Yeah.
Okay. Are you able to manipulate it at all? So like, if you have the same biomass starting material, let's say, relatively the same, probably some variation, but can you direct it to one way or another depending on how you do the drying and the pyrolysis steps?
Yeah. So as like, let's say, for example, if you're using a hardwood, you're going to get a biochar that has more carboxylic acids, probably more phenol type materials, probably like this bottom left example.
Mm-hmm.
But this is maybe 400, 350, 400, 500 degrees Celsius. If you go up to 600, 700 degrees Celsius, you start to remove those functional groups and you get more of a fixed carbon structure like graphene. So we've done some work to show it. The difficult thing is that you're always dealing with a heterogeneous starting material. So you may have a piece of the wood that just had more lignin or more cellulose. And so you can't tell that. I mean, you could do like a molecular study and say, like, every time I have this much lignin or cellulose, I'm going to get this much oxygen functionality. But it's not practical for
Yeah,
the actual
absolutely.
application. Yeah.
Okay. All right. That's interesting. Can you talk a little bit more about the drying process itself?
Yeah. I mean, it's not very exciting in terms of what we currently do. So where did I go with that? We take the wet, gross, we get this stuff frozen for the crab, and then we put it out on sheets and dry it in the oven. And just dry it. We did some optimization we want to make sure that we have less than 20% water content. Because otherwise this is going to get moldy and
it's not good.
yeah. But I mean, this is the bottleneck of this whole process. We're actually so this is all really, it's pretty interesting because you're working with industries along the way who are interested in the actual outcomes of these research projects. So we're working with right now a local paper mill who produces pulp and paper. And they produce 30% extra heat or energy than they can actually use on a daily basis. Yeah. And they're on our island. And so the 5 local crabbing industries are chatting with this industry to see if there was potential to use their excess heat for this drying process. Because if we can reduce the cost of this and we can get to a stable, solid, ground up product that we can store, maybe we pyrolyze it, but maybe we don't. Maybe this is the product. You can extract chitin from this. You could use this as your soil amendment. There's a lot of value in this dried product as well.
That's super interesting. I mean, that's a great point. If you have this excess, stuff that's going to be wasted anyway, why not try and make good use of it? That's really smart.
Yeah,
okay.
Exactly.
So you talked about the higher heating value in the crab oil. Do you know why it's higher?
I suspect that it is higher than than woody biomass because of the fact that it's coming from a really basic starting material. And so we're getting generation of less sort of corrosive, decompostable materials. So when you have acetic acid present in your bio oil, it is corrosive to the bio oil itself as well. So it'll decompose quickly. It'll break down a lot of the higher molecular weight molecules that you want to have present. You want to have basically bio oil. You want to have like higher molecular weight molecules that have stored energy to burn. And if you have an acid present in that oil, it starts to break those down. So I think that that's where that comes from, but we don't know for sure. We're actually really excited this summer. One of our goals is to get a really good idea about the chemical composition of the crab oil because it's unknown. We know some of the stuff that's in there, but we don't know what the major components are. So we're really excited about that.
That'd be very cool.
Yeah.
Let's see. Have you looked at pyrolysis pressure / back pressure to see if that changes the ratio of solid, liquid, and gas?
Yeah. So we always keep a negative pressure. I don't have any pictures of our systems. I should. They're not impressive though. Like they're really, we built them ourselves. One of them just looks like a giant marshmallow. We keep a negative pressure because we recycle our syngas back through. We don't burn it, but we just recycle it back through in order to push the oxygen out. We don't measure the pressure though. So I am sure there's literature out there that does look at the effect of pressure in really controlled systems, but we've never looked at that in our lab.
Okay.
Yep.
And this is probably the last question unless somebody gets one in.
Sure.
Does the introduction of the crab char to the acidic mining waste generate any new product?
Yeah, that's a great question. Definitely. So the calcium carbonate is reacting with the copper and the iron that's in solution, probably the aluminum and magnesium as well. We did some work to look at using David Hopkins, who's the first author on this paper, he did some work looking at using XPS and XRD to look at what the salts were that were forming when you add crab char to we didn't actually use acid mine water in that study. We used doped solutions that were acidic that contain just one iron salt or just one calcium salt.
Okay.
And we definitely see ionic exchange. So we're making new salts, and that's essentially how the neutralization process happens. But we don't have a good handle on what would happen if we add crab char to a real acid mine. Like we have done that, but we haven't studied what the outcome of all the salts. It's a very complicated system. So we don't know what all the resulting salts are going to be when you have everything present that's in the acid mine solution. But it's a really important question that we need to answer, because just neutralizing the pH is not enough. It's going to help, but we have to be able to contain and change these corrosive elements into something that's non-toxic.
Sure. So I guess I'll ask a follow-up on that.
Sure.
So you mentioned the porous structure of the biochar. Is there any so I know, like, for instance, like activated charcoal, for instance, right? It has pores, and you can trap molecules and things like that inside the pores, and that's sort of how it works, right? Is there any similar effect with the biochar at all, or is it almost entirely the ion exchange?
Yeah, it's a great question. So I have another PowerPoint open
Awesome.
here.
Good.
So we did a bunch of work looking at characterizing the biochar. This is woody biomass. Honestly, the crab biochar is mostly calcium carbonate. So it's not very porous.
Okay.
But the woody biomass is much more interesting in terms of porosity. So you see these, it almost looks like a molecular sponge. This is an SEM image.
Yeah.
You see big pores and little pores, and there is pores that go between the pores as well. The surface areas are much higher. So we took this biochar and we absorbed a whole bunch of different metal salts from solution.
Okay.
And it has a great affinity for iron and lead. And that was really interesting to us from a chemical perspective. We wanted to understand what was happening. It has a good affinity for all metals. And we saw some weird stuff going on with manganese, but I think it was probably oxidizing, crashing into solution. And so we spent quite a lot of time, doing some modeling to look at what the impact of, so trying to understand like the isotherms, how are these metals being absorbed? Can we get an idea of the mechanism of absorption? So of course, we thought there were possible 3 options. We could have absorption through like a physical absorption where it's being trapped in the pores, as you had suggested, like almost like a sponge. Because we know that there are surface functional groups, there might be some chemical absorption of the metals, like through sort of ligand metal interactions, but there can also be precipitation because all of these metals can form oxides that can precipitate out of solution and then stick to the material. So we did some XPS to look at that. So this is a lot of data, but I'll try to summarize it in something that makes sense here. We saw by XPS. XPS is a surface. Do you know what XPS is? It's a surface technique that just tells you kind of the environment that the metal is most likely in.
Okay.
So we saw all the metals we added to the char were present in their original form. So the metal 2+ ions makes sense. So that means that we're getting some physical absorption of the metals themselves.
Sure.
We also see the formation of some insoluble oxides. So they're oxidizing with the air and then they're precipitating out. They're making nanoparticles and they're getting caught in the pores or they're getting stuck to the surface for the iron, copper, nickel, and lead. But what was really cool is that we actually saw evidence that we get some metal ligand interaction. So because we have these oxygen surface groups that I've talked about so much, we actually saw evidence of these acetate, metal acetate ligand molecules on the surface of the biochar as well. And so that indicates that we also have chemical absorption happening. So we've done some work. We published this work in the Journal of Physical Chemistry a couple of years ago now to show that there are all 3 modes are most likely happening, and you can see that through the XPS evidence. So that was pretty cool.
That is very cool. That's really neat. It's amazing that you see all 3 of the modes too. That's I guess fairly unusual, but I mean you have clear evidence for all 3.
Yeah,
really interesting.
We didn't expect this. I mean, this was just really neat to see. I mean, I definitely expected to see oxides formed because I could actually see iron oxide forming. It's orange precipitate, but we didn't expect to see the acetates forming. I knew that there was surface carboxylate groups because, of course, if you think about the fact that when you burn wood, especially hardwood, you make a bio-oil that has a high concentration of acetic acid. So the surface of the biochar is also going to have a reasonably high concentration of carboxylate groups.
Makes sense.
Yeah. And so it was kind of cool to see these metal carboxylate interactions, and also cool to see that they match up with what you would expect to bind to carboxylates. So copper acetate, nickel acetate, zinc acetate, cadmium acetate, they're salts that wouldn't be surprising to see formed anyways. So it was kind of neat to see that those metals in particular do make the acetate metal ligand interaction.
Oh, that's super cool. That's really cool. Fantastic. So I think that's all the questions we've got. So I will say thank you one more time for a fantastic talk, and additional slides from other talks too to follow up with some more details. That was super cool.
Awesome.
And I really appreciate you taking the time again to give this talk. And so if I can get you to hang around for just 1 second, we'll talk very briefly, and then For everybody that's watching, thank you for coming out. Really appreciate it. And I think we don't have a talking scheduled for next week, but one for the week after that. So I hope you'll come back and join us then. And otherwise, have a good weekend. Stay safe. See you next time. Everybody for coming out. And thanks again to our speaker, Dr. MacQuarrie.
Thanks for having me. It was great.